Okay, error estimation. We can use the integral test to tell if a sum evaluated to infinity is going to converge or diverge. But we can also use the same approach to get an estimate of error. Error in what? Well, let's imagine that we have something that we're going to sum over, and let's say n is equal to 1 of a sub n, but now we're not going to infinity. We're going to some number that we can then calculate each value. Let's say 10. I just made that up. We're going to take the first 10 elements of this infinite series and sum them all together and get this is equal to some sum. Okay? And that's a number. We can calculate that. But the question is, what is the error term around this? So this is going to be plus or minus some error term compared to if we had actually gone to infinity. Okay, so that's what we're talking about. When we're saying error estimation, we're trying to estimate the error of a partial sum compared to the total sum. So we can't calculate analytically what the total sum would be. We're just going to estimate it by using a partial sum, in other words, the first x number of elements in the sequence, and add those together. But to make it a little bit nicer, we're also going to do an error estimation. Now, where does this error estimation come from? Well, it comes from calculus. And basically what we do is we look down here at these little diagrams that I've made up. And let us say that in this case, our partial sum is just the first three elements, A1, A2, A3. Okay, we sum those together, and that's our estimate. Now, what about our error? How are we going to get at that? And what we're going to do basically is sandwich it between two values, two integral calculations. The first calculation is we're going to look at the integration of our term. Let's say that this is, once again, f of x. So we integrate f of x dx from, in our case, since we did the first three elements, we'll do it from 3 to infinity. Okay? And you can see that what that's going to do is it's going to give the area under the curve from this point on. So all this area down here. You'll notice that A4, A5, A6 occur below the curve. Therefore, this estimate here is a bit of a overestimate of what the sum of the remainder would be. This term, we're going to say, is going to be greater than the remainder that's left. And that remainder is obviously going to be, I'll just put it in brackets here, the sum from n is equal to 4 to infinity of our terms. Okay? Now, the second way we might look at it is, well, let's just say we're going to do one extra element over. Okay? In this case, we're going to integrate from 4 to infinity of our function f of x dx. Now, that's the area off to the right there. Now, what has that done for us? We've moved it up by 1. We've gone from, k elements. Now we're going to start at k plus 1. Okay, I see that. But why did we do that? Well, now what you have to imagine is taking these rectangles that represent A4, A5, A6 and shifting them to the right by 1 unit. That's what I did over here. There's A4, it's been shifted, so now it's not setting between 3 and 4, it's setting between 4 and 5. See how that moved over? Now notice that there's now again a one-to-one correspondence going off to infinity, and in each case, each of these rectangles is a bit bigger than the area under the curve for that interval. That means that our remainder, in other words, a4 plus a5 plus a6 on to infinity, is going to be greater than this integral here. So we'll have to say that the remainder is greater than this term. Therefore, we created a sandwich. This value here is larger than the remainder. This value is smaller than the remainder. And from that we can get we'll take our estimate, our partial sum, and then we'll know the range around it that our true value must fall into.